Well, thank you for having me speak here. I think it's a great format, and I will talk about what we do in my group in nanomaterials. And inspired by previous CHEM talks, I thought I would start a little bit with how I got here. I got my PhD in 2013 from Aarhus University. I was in Aarhus for all of my education, so from my bachelor's to my PhD, and worked in Center for Materials Crystallography, a center of excellence. And my supervisor was Bo Iversen, and Bo had a large group doing all kinds of materials and focusing a lot of crystallography. And that's of course some of the work I inspired by that I still do now. So after my PhD in 2013, I went to New York as a postdoc. I was funded by the Willem Foundation and got 2 years of funding to work at Department of Applied Physics, actually. So I went from a chemistry department to a physics department with Simon Billench, who is a pioneer in X-ray scattering, and especially in the total scattering methods that I'll talk to you about. And after that, I got my position here. So I came here on the tenure track program, and I started in October 2015. This was the first group photo that we did in May 2016. And then since then, the group has grown, and I've been lucky to work with fantastic students since I arrived here. And I'll today show some of the work, mostly from the past couple of years that we've done in the group. So we're materials chemists, and that means that we're interested in understanding how we can develop and improve the materials, so functional materials that we have around us. So if we consider first because we have functional materials around us and we have fantastic materials, and if we consider the development that has happened there, well, it usually starts by someone going to the lab. So someone does an experiment in the lab, and then what you can do is that you can go to maybe a different lab, and then you can characterize what you've made. And quite often what you will characterize first when it comes to materials is atomic structure. And this will be done by crystallography, so usually by X-ray diffraction. Then you can characterize properties, and then by combining all of these things, so material synthesis to properties, well, then you can get some understanding, and then you can start over and make even better materials. So there's no crystallography has played an enormous role in developing what we have today. Now, a lot of the materials that we are studying now, generally in materials chemistry, are nanomaterials. And we know that we can make different materials, and we know that we can make different properties. But of course, one of the issues is actually characterizing these. We can engineer structures at the nanoscale, but can we actually determine their atomic structure? Because it's this understanding of the relation between structure and properties that allow us to develop materials. Because the problem is, if I compare here to diffraction, as is usually used for structural characterization from a bulk material, well, then nanomaterials scatter something like this. So instead of these nice sharp Bragg peaks that we use in crystallography to characterize material structure, then nanomaterials, here cadmium selenide nanoparticles, will give features like this, which can be much more difficult to extract quantitative structural information from. And that's what we're interested in. Because this means, so this, we call it the nanostructure problem, means that if we cannot characterize atomic structure, then what we can do is that we can do material synthesis and we can test properties, but obtaining this understanding, which is needed for the next step, well, that's a problem, and this is the nanostructure problem. And I'll show you some examples of how we solve it, because right now, instead of what is basically just being done is to assume that the structure of a nanoparticle is basically the same as the structure of the bulk crystal structure, but that we just cut it out of the material. For example, a material that we have studied quite a lot is tungsten oxide. So tungsten oxides have lots of applications, for example, in photocatalysis, but also in battery science. And it can be synthesized in quite a lot of different polymorphs, meaning that we can make different crystal structures. So here are just some that are shown, that we can look these up in databases. so the fully oxidized tungsten oxide and these non-stoichiometric phases and a hydrate. And these are just examples of what can be made. And these have quite different properties. So it's important that when we synthesize the materials, well, we know what we're getting. And a nanomaterial that has been studied quite a lot in this context is small nanorods. So you can make nanorods of tungsten oxide. And here's just a few XRD patterns, so X-ray diffraction patterns from somewhat recent literature. This is an older version, but also in recent high impact literature, showing their XRD patterns from these nanorods, as well as then the reference compound, which is tungsten 18049. So it's this structure here. And when you look at this, so this is the calculated pattern, right? So the way this is usually done is just to compare where peak positions are. And it's really hard to say. We can say there is a peak here, right? But the rest just contains a lot of smeared out structural information. So assigning a structure to this is quite difficult. And we would like to sort of change that so that we can actually find out what is the atomic arrangements in these nanorods. So we need a different method than just this conventional powder diffraction, which is usually used for crystalline materials. So we wanted to investigate these, and my former PhD student, Mikkel, he went to the lab and developed a synthesis where we could, super simple, take ammonium metatungstate in some different organic solvents, and by changing the concentration of the ammonium metatungstate, well, he could get different kinds of particles out. So these up here, we'll talk about first. They have these sort of characteristic somewhat bright-like peaks, and then down here when we have lower concentration one, then it's just these broad features. And here's some TM images of, I think, this sample here. So we can make these nanorods, which we wanted to investigate. And if we didn't do sort of the conventional way, well, then we just compare our data to reference compounds, so to calculated PXRD patterns from different structures. And you can see it's really difficult to make this fingerprint, as we can usually do for crystalline materials, because we just have really broad peaks, and all of these materials actually have somewhat of a peak where we see this. So we go to a different method. We use what we call total scattering and PDF analysis, because as you can see, there is information in this scattering pattern. It's just about getting it out beyond sort of bright peaks. So the way we like to treat these data is to take our total scattering data and then Fourier transform them. So the Fourier transform means that we go from Q space, or scattering space, or reciprocal space, if any of you have taken crystallography courses. Well, then we go from Q space, which can be a little bit hard to interpret, to R space, so we're in real space. And that means we now get a much more intuitive function that we can analyze. So in this, we can talk about this, and we call this the PDF, the pair distribution function. And we can analyze this in the structure, or we can first find out what it actually is. Because imagine first I have a structure consisting of these two atoms, here separated by a distance R0. Well, the PDF from this structure would give one peak in R at R0. And then probably my atoms would vibrate a little bit. So then I would get a broadening of my PDF peaks, because it basically just represents a histogram of the interatomic distances that I have in my sample. And if we do it for here 2D sample, well, then I would see a PDF peak as the first interatomic distance here, and here, and here, and here, and so on. So it's a fairly intuitive way of analyzing scattering data. So we had these tungsten oxide structures, and we can then look now if instead of being in Q space, in scattering space, can I actually distinguish between the structures in R space? So here I have some of these structures that we were looking at before. So the monoclinic tungsten oxide and different stoichiometries here. And the PDFs are then represented here. And the first peak in these structures will then be a tungsten oxygen distance, because that's basically always going to be the same distance, the distance between a tungsten and an oxygen atom. Then we're going to have different peaks out here. So the second peak here, that's a tungsten-tungsten distance in edge-sharing octahedra, as we have them here or here. And then the next one is in corner-sharing octahedra. So these structures, they will have different ratios of this peak, because we have different amounts of edge and covalent sharing octahedra. And then, of course, there's also distances that are different out here, further out in the structure, because that's where we start having the arrangement of all of these polyhedra sitting together. We also, in tungsten oxide, so these were solid states, or solid state structures, but you can also make what's called polyoxymetallates, which are very well known in organic ions, like these large ions here. And we can actually also distinguish these from PDF, and we'll get to that in a little bit. Okay, so these are the Q-space data, and then we went to a synchrotron to collect these because we need high quality, high energy synchrotron data to do PDF. And then, well, we could get these PDFs as we have here, and now we can start analyzing them and understanding the structures of the nanorods. So we start with these nanorods here. So usually in the literature, what's represented or what's assumed is that it takes these nanorods take the tungsten 18049 structure. And here we've taken the experimental PDF in blue, and then the calculated PDF in red from this structure, and then a difference curve. And we see that it fits fairly well. It's okay. We can also take a different structure, which is somewhat related. So tungsten 10029, instead of these pentagonal columns, as we'll get back to, well, we have these sphere planes, and this fits somewhat worse. We don't get the same description of everything. But what we were then trying to do, or what Mikkel was trying to do, is just consider, can we improve this fit? Because there's definitely things that are not fitting here. And we went through a lot of different structures, also including elements with similar chemistry, for example, niobium. And we found out that we could actually get a nice description of these nanorods if we took a niobium tungstate structure, which has this structure here, and substituted with niobium with tungsten. So we just use a structure from a slightly different chemical system. And then we can describe this in much more detail. So when we analyze things like this, it's important to sort of know the limit of information that is in the PDF and how much can we get out of it. And that's something we're working on a lot, also using statistical methods for this. But what we found was that what we can conclude is that these structures have a high concentration of what these pentagonal columns, where we have these octahedra arranged in these sort of flower-like structures here. So we can get at least an idea of the structural motifs that are important in the material, and then we can start analyzing that in more detail and correlating with properties. And Mikkel also analyzed sort of the size of the rods with this PDF, but we'll skip that. So these were the large structures, so we could establish the structure of the nanorods, but we also had these much smaller particles, which we were synthesizing with lower concentrations. And here what we did was to collect data PDF data from them, and we had these PDFs here, so 5 millimolar and 10 millimolar, and you see we only have sort of local structure, clear PDF peaks at very low R values. And that means that in the structure, we only have ordering of the atoms very locally. And this is consistent with an amorphous structure. But we could then use a different method, which is small angle scattering. And the small angle scattering will instead give us not the atomic ordering, but the size of the individual particles. And this is sex data, and it's not so important, but what we could find is that if we analyze the used sex to find a size, well, then this is the size here plotted on the PDF scale. So that again shows that we have amorphous particles because they're much larger than the extent of ordering in the materials. And we can also start analyzing then these peaks here that we had at lower R here to understand what is the atomic arrangement in the amorphous materials. And what we did here was to, again, like we said before, to test a lot of different structures and see what happens and see how it fits. But we found that none of the crystalline structures that are known could describe the structure of these amorphous nanoparticles. So instead, what we did was considering what other tungsten oxide structures do we know? And as briefly mentioned, when you dissolve tungsten oxides in aqueous solutions at different pH values, you can stabilize different polyoxymetallates. So these kinds of ions here, or structures, which are then large ions, which can be stabilized in different coordinations. And the synthesis was done from a solution of ammonium metatungstate, where metatungstate is showed here. So first we tried to fit the PDF with a metatungstate, and that really doesn't go so well. There's definitely peaks that we don't have. But if we consider then the paratungstate, well, which is a different cluster, which we have also worked with before, well, then we see that at least some of the peaks are there. Now, we don't really believe that we have these large irons in the amorphous material, but what we think is that the local chemistry of the amorphous particles probably has chemistry that's related to these, because it's how many different ways can you organize tungsten polyhedra or tungsten oxide polyhedra. So what we did was to do a lot of modeling again, and we cut out these fragments, and we tried a lot of different fragments to see that if we have this local structure, well, then we can actually fit the PDF, or the PDF from these amorphous nanoparticles. So that's what we gain, that we can get a motif that will dominate in the local ordering of the nanoparticles. And this is the way that we can, in similar ways, we can characterize a lot of nanomaterials, and therefore be able to correlate this sort of synthesis structure and properties relationship. And we've done this on quite a few different kinds of materials. And I won't go through more of the examples here, but just sort of the main thing that we're learning is that when we go to the nanoscale, well, then defects that are actually well known from both materials completely dominate and sort of take over what then turns into the average or medium range structure in the nanomaterials. And that gives us some insight onto how we can design materials, or what structures we can expect when we synthesize very small nanoparticles and get these size-dependent materials. Okay, so another thing that we're really interested in, of course, is how can we control what forms in these syntheses? Because now what we've done is to do a synthesis, and let's go to the lab and do something, but can we control or predict what happens when you do a synthesis? Because if we again come back to this sort of material develop timeline, then for the past couple of decades, what has been discussed a lot in materials chemistry, or sort of a term that is used a lot, is this idea about materials by design. So if you want to make a specific a material with specific properties, well, then we can sort of start imagining how should I put my atoms together and to get those properties. Now, the problem with, or this is of course wonderful, but the challenge here is that the material synthesis is not always as following those same sort of design principles. At least in my lab, there's a lot of trial and error going on when we want to synthesize a new material, because we have very little understanding on how atoms actually come together and form these materials. We always sort of compare this to organic synthesis, where I was taught when I did organic chemistry courses that you can somewhat predict how your molecules will react. We're not quite there in solid state chemistry or the formation of these materials. So we really want some atomic insight into these nucleation processes, and that's also some of what we're doing in my group. And I'll give an example of this for a synthesis of a related material, so niobium oxide nanoparticles. So again, just as tungsten oxide, niobium oxide has a ton of different polymorphs. So these are some of the ones, and just a fraction really, of niobium oxides that are reported in databases. Niobium oxides has been or have been receiving a ton of attention recently, because it's been discovered that they are very, very good for high rate lithium-ion batteries. So you can get a lot of lithium in very quickly. But again, here we have a lack of understanding of how we can form a specific polymorph, and actually also of the structures of them. For those of you that are used to looking at unit cells and materials, you see something like this really looks fairly funky and maybe not so physical. So there's a lot of work to be done in understanding the structure of these. But we wanted to see how a specific polymorph comes along. Well, we can first just see a little bit about the structure types. So a lot of these materials are based on a very simple structure motif, which is this unit cell here. This is called the rhenium oxide structure, and it's just sort of these 4 or 8 niobium oxygen polyhedra that is sitting together in this simple way. And now if you take this structure and you can do different kinds of sort of defects, or you can make defects in it, then you can get this tetragonal tungsten bronze type structure. Or you can shear, so you can sort of move some of these polyhedra, and you get shear planes. Or you can shear in 2 dimensions, and then you get Watchley rod structures that are shown here. And niobium oxide forms especially these Watchley rod structures, which we wanted to investigate. So this is my PhD student Olivia, who has been working on this, and we wanted to study a fairly simple synthesis method, which is actually used for making a lot of different oxides. You take a chloride salt, and then you put it in benzyl alcohol, and then it's a solver thermal reaction. So you heat it and you keep it under pressure, and then nanoparticles form. And this has been studied for a lot of different oxides, because you can make fairly high quality nanoparticles in this very simple way. So we took our synthesis and did it sort of studied this in situ. So we shoot X-rays on it at the same time as the synthesis goes on, and then we can collect data and follow the reaction. So the way this is, or the data that we get out from this is something like this. So here we have Q, so could also just think of it as a scattering angle, and then time, and then intensity is shown in this contour plot. So what we see here is that in the beginning, down here at 0 minutes, we have only sort of these broad diffuse scattering where there's no bragg peaks. And then after a little while, well, we get some broad bragg peaks. And we can also look at this in PDF, but I think I have this in the next one. So we can see the structural differences between the precursor, luckily, and the end product. So here's if I take the PDF here after a minute, then it's this one that we plotted here. And again, we tried a lot of different models, and the most obvious one is this HNB205. This is the structure shown here, and this is the thermodynamically stable niobium oxide structure. And what we found was that the first product that appears, so after 1 minute of reaction, well, we can actually fit that fairly well with this model, and we describe all of the main PDF peaks. But after the materials have grown, so after the nanoparticles have grown a little bit, well, then we don't fit all of this that is out in the PDF. So that shows that the HNB205 model is a bad model to describe the particles that we have here after 24 minutes. We can also see this, and this is a little bit more technical, but we can see that in fit quality that it really doesn't fit. So we were thinking about what else to do. And when we were looking at this fit, what was not fitting was the amount of these edge sharing octahedra that appear in the structure. So in the experimental data, we saw we needed more edge sharing than corner sharing or than we had in this material. So we were looking at different structures. So here we have the ideal HNB205 material that is known from the literature. But what we found was that maybe what was missing was that the sizes of these domains of this rhenium oxide structure were not really corresponding to what we saw in our nanoparticles. So we would like to develop a simple model where we could model this. And I don't have to go into details with this, but we found that we could, by combining 2 models representing both the sort of the inner core of these Watchley rod structures and the edges around, well, then we could actually get a fairly good description. We'll come back to this in a little bit. So we can look at the crystalline structures, and we can look at how defects develop in the crystalline structures and nanocrystalline structures. But of course, what we're also interested in are the very, very early stages of the material formation. And here we show the PDFs that are obtained then from an experiment at 100 degrees, so it's lower temperatures than before, where we can follow this because it's lower temperature at a little bit slower fashion. So again, here I have times, so 0 minutes, and here we have the PDF. And our precursor for this is niobium chloride that we dissolve in benzyl alcohol. And if you look at these PDFs here, and this is the same up here, well, there's a fairly sharp peak here at about 2.3 angstrom. And 2.3 angstrom, that corresponds perfectly to a distance between a niobium atom and a chloride ion here in this precursor. But we also see a little peak here, and that's 2.0 angstrom, and that corresponds then to a niobium oxygen distance. So what we could do is try to start making models for this, because the hypothesis for the reaction mechanism is that this oxygen here will coordinate to the niobium, and then make this will act as a leaving group in the reaction. So we could start modeling these data here with different sizes of clusters. So here we could model the first peak, this is our first PDF, this is the precursor. And then 1 minute into the reaction, well, we could see we had a peak forming here. That's a niobium distance. So that shows that we start having larger clusters formed. And then later into the reaction, well, we can start modeling these with some larger clusters. And what's important was that what we found is that the reaction mechanism happens where these conus sharing octahedra sort of find each other first, and then much later on we get edge sharing octahedra that then continue to develop. So that's sort of the things that we can learn from an experiment like this, that from the niobium chloride 6 precursor we can substitute chloride with oxygen from the benzyl alcohol, and as soon as this happens we see the formation of these niobium and niobium pairs. So we see that we have them connected. And then we nucleate this niobium oxide structure in this structure here, and then we form the next level and form starting these edge sharing octahedra, and then we get a defect structure in the end. And now what we can see is that the defect density is affected by the synthesis conditions. And now, of course, the next question is, can we then use that information to actually control the structure of the material? And we do a lot of these in situ studies, and we learn a lot of reaction mechanisms from it. But of course, PDF is our main tool for this, and we love PDF, but there's also a lot of sort of bottlenecks and a lot of problems in the technique. Because I said before that this is an intuitive method of analyzing structure-wise, but you can usually say what the first couple of peaks are, but when we get further into our space, well, then it gets much harder to assign those. So we always end up sitting and testing a million different structures, or tens or hundreds of different structures, and seeing what fits best. So what we are working a lot on is to sort of automate these methods here. And I think I'm much slower than we expected. So I'll skip this next example actually, although it's super fun. But just say that is something that we're working a lot on to try and see can we do database mining? So can I extract a ton of structures from the database which now exist, and then fit them all to my PDF, and then just see what fits best and take that structure and work on it further. And that we've been doing for a couple of years, and we have some papers out where we do this sort of automated modeling and structure mining. And when we were doing this, I had a couple of students who said, well, they had taken a machine learning course over at computer science, and this is a perfect example of something we can use machine learning for, because then instead of doing the sort of the brute force method of just testing a lot of structures, well, then we can give those results from maybe 10,000 structures to a machine learning algorithm, and then that can learn what kind of structures actually fit. And we're working on different ways of doing this, where we also use what's called interpretive machine learning methods, so that we can actually find out why a specific structure also seems to be giving a better model. And this is, you can find an example of this here in a recent paper we just put on arXiv last week. So this idea is sort of automated modeling, and can we do some of the stuff that we right now do manually, and we use machine learning for this. We also have different projects where we, instead of having to go through a lot of different structures, can maybe start solving atomic structures from PDF directly. And this is something we've also been working on in a collaboration with computer science for sort of learning how to do structure solution from PDF, or we just give the machine a PDF and then it gives us a solution. And that's another paper that we have on arXiv, where we are able to do this for some very simple structures, monometallic nanoparticles. And I'll just make advertisement for Ulrich is talking about a related project on Friday at the Nanoscience student seminar. That's our symposium that's coming up on Friday. One thing I haven't mentioned at all, but I thought I needed at least one slide just to say that this is something that we're now doing, is of course high entropy alloys and high entropy oxides. So my group is part of CHEM, so Center for High Entropy Alloy Catalysis. And in CHEM, what we're doing is exploring these new kinds of materials for electrocatalysis. So on a high entropy material, you have five or more different elements that sit in an ordered lattice. So this is a metal, right? So an FCC, and you can put a lot of different metals on the sides. In an oxide, you do the same, but just in an oxide structure. And in CHEM, we're my group in particular, or sort of in collaboration with these in my group, we study how we can synthesize high entropy materials, what controls their formation, and how the synthesis method influences structure. So a lot of the same sort of themes that we've seen in the example so far. And with that, I think my time is up. So I just want to thank the people that contributed. So I mostly showed work from Mikkel, who's now in Oxford, and current students Olivia, Emil, and Andy, and the rest of the group, and collaborators at computer science in particular. And this is the group, and I have open PhD fellowships. And thank you for your attention.